What is insulin resistance? In fact, what exactly is diabetes? What causes it? Studies dating back nearly a century noted a striking finding. If you take young, healthy people, split them up into two groups, half on a fat-rich diet and half on a carb-rich diet, within just 2 days, this is what happens. The glucose intolerance skyrockets in the fat group. In response to the same sugar water challenge, the group that had been blood sugar. As the amount of fat in the diet goes up, so does one's blood sugar spikes. It would take scientists nearly 7 decades to unravel the mystery, but it would end up holding the key to our current understanding of the cause of type 2 diabetes. The reason athletes carb load before a race is that they're trying to build up a fuel supply in their muscles. We break down starch into glucose in our digestive tract. It circulates as blood glucose, blood sugar, and is taken up by our muscles to be stored or burned for energy. Blood sugar, though, is like a vampire. It needs an invitation to come into our cells, and that invitation is insulin. Here's a muscle cell. Here's some blood sugar waiting outside patiently to come in. Insulin is the key that unlocks the door to let the glucose in the blood enter the muscle cell. When insulin attaches to the insulin receptor, which activates glucose transport, where it acts as a gateway for glucose to enter into the cell. So insulin is the key that unlocks the door into our muscle cells for blood sugar. What if there's no insulin, though? Our blood sugar would just get stuck out in the bloodstream, banging on the door to our muscles, not be able to get inside, and so with nowhere to go, blood sugar levels would rise and rise, and that's what happens in type 1 diabetes. The cells in the pancreas just don't make insulin. The cells that do make insulin get destroyed into the blood, into the muscles, and blood sugar rises. But there's a second way we could end up with high blood sugar. What if there's enough insulin, but the insulin doesn't work? The key is there, but something's gummed up the lock. This is called insulin resistance. Our muscles become resistant to the effect of insulin. What's gumming up the door locks to our muscle cells, preventing insulin from letting glucose in? Fat. Intramyocellular lipid, fat inside our muscle cells. Fat in the bloodstream can build up inside the muscle cell and create these breakdown products and free radicals that can block the insulin signaling process. So no matter how much insulin we have in our blood, it's not able to open up the glucose gates and blood sugar levels build up in the blood. This mechanism by which fat induces insulin resistance wasn't known until fancy MRI techniques were developed to see what's happening inside people's muscles as fat is infused into their bloodstream. That's how we found out that elevation of fat levels in the blood causes insulin resistance by the inhibition of glucose transport into our muscles. And this can happen within 3 hours. One hit of fat can start causing insulin resistance, inhibiting glucose uptake within just 160 minutes. Same thing happens to teens. You infuse fat into their bloodstream, and it builds up in their muscles and decreases insulin sensitivity, showing that increased fat in the blood is an important contributor to insulin resistance. And then you can do the opposite experiment. Lower the level of fat in people's blood, and the insulin resistance comes right down. Clear the fat out of the blood, and you can clear the sugar out of the blood. So that explains this finding. On the high-fat ketogenic diet, insulin doesn't work as well. Our bodies are insulin resistant. But as the amount of fat in our diet gets lower and lower, insulin works better and better. A clear demonstration that the sugar tolerance of even healthy individuals can be impaired by administering a low-carb, high-fat diet. But we can decrease insulin resistance by decreasing fat intake. As the level of fat rises, the body's ability to clear sugar from the blood drops. Now, where does this fat in our blood that's wreaking all this havoc come from? Well, it comes from the fat we eat as well as from the fat we wear. The number of fat cells we have stays constant in adulthood. It's interesting. The way they figure that out is actually by measuring the amount of radioactive carbon trapped in our DNA from all the nuclear bomb tests. They can actually measure it that way. Anyway, after massive weight loss, our fat stays the same. Conversely, as we gain weight, our fat cells just stretch as we pack more and more fat into each individual fat cell. So when our, belly button thighs gets big, we're not adding more fat cells, we're just cramming more fat into each cell. And at a certain point, our cells become so bloated that they start spilling fat back into the bloodstream. This is an illustration of the so-called spillover effect. Not only do obese persons have more fat, they're constantly spilling that fat into their bloodstream. So that could explain the link between obesity and diabetes. Fat is spilling from our fat cells and gets lodged in our muscle cells, leading to the insulin resistance that promotes the onset of type 2 diabetes. Or, of course, the fat can enter our bloodstream through our mouth. If you put people on a low-carb diet, fat builds up in our muscles within 2 hours compared to a low-fat diet, and insulin sensitivity drops. And the more fat in our muscles, the lower the ability to clear fat from the blood. It doesn't take years for that to happen, just hours after these foods go into our mouths. A fat-rich diet can increase fat in the blood, and this increase is accompanied by a decrease in insulin sensitivity. Studies clearly demonstrate that fat in the blood directly inhibits glucose transport and usage in our muscles, which is responsible for clearing about 85% of the glucose out of our blood. So these findings also indicate an important role of nutrition, particularly increased consumption of fat, for the development of insulin resistance. Normally, we only have between 1 and 500 micromoles of free fat floating around our bloodstream at any one time, but those who are obese, constantly spilling fat into their bloodstream, as you can see, have much higher levels. But we can reach those same levels eating a high-fat diet. So a skinny person eating a low-carb diet can have the same level of fat in their blood as an obese person does. Similarly, being obese is like eating, or even if you're eating healthy, because you're spilling fat from your own fat cells into the bloodstream no matter what goes into your mouth. The association between fat and insulin resistance is now widely accepted, so-called ectopic fat accumulation, the accumulation of fat in places that it's not supposed to be, like within our muscle cells. But not all fats affect muscles the same. The type of fat, saturated versus unsaturated, is critical. Saturated fat, like palmitate, is found mostly in meat, dairy, and eggs, causes insulin resistance, whereas oleate, found mostly in nuts, olives, avocados, actually improve insulin sensitivity. What makes saturated fat bad? Well, saturated fat causes more of these toxic breakdown products and mitochondrial dysfunction, and increases oxidative stress and inflammation, establishing a vicious cycle of events in which saturated fat-induced free radicals causes dysfunction in little power plants within our cells, the mitochondria, which causes further increase in free radical production and impairment of insulin signaling. Fat cells filled with saturated fat activate an inflammatory response to a far greater fat has been demonstrated to raise insulin resistance through free radical and ceramide production. Saturated fat also has been shown to have more of a direct effect on skeletal muscle insulin resistance. Accumulation of saturated fat increases the amount of diacylglycerol in our muscles, which has been demonstrated to have a potent effect on muscle insulin resistance. It doesn't matter if the fat in our blood comes from our fat or from their fat in our diet. You can take muscle biopsies from people and correlate the saturated fat buildup in their muscles with insulin resistance, while monounsaturated fats are more likely to be detoxified or kind of safely stored away. Saturated fats create these toxic breakdown products like ceramide that increases lipotoxicity. Lipo meaning fat, like as in liposuction, and toxicity. This fat toxicity in our muscles is a well-known concept for the explanation for this trigger of insulin resistance. We talked about the role of saturated trans fats contributing to the progression of other diseases like autoimmune diseases, cancer, heart disease, but they can also cause insulin resistance, the underlying cause of prediabetes. Human diet, saturated fats are derived from animal sources, while trans fats originate in meat and milk, in addition to the partially hydrogenated and refined vegetable oils as well. That's why experimentally shifting people from animal fats to plant fats can improve insulin sensitivity. Insulin sensitivity was impaired on the diet with added butter fat, but not with added olive fat, for example, in this study. We know prolonged exposure of our muscles to high levels of fat leads to severe insulin resistance, with saturated fats demonstrated to be the worst. They don't just lead to inhibition of insulin signaling, the activation of inflammatory pathways, and this increase in free radicals. They cause an alteration in gene expression, leading to a suppression of key mitochondrial enzymes like carnitine palmitoyltransferase, which finally solves the mystery of why those eating vegetarian have a 60% higher expression of the fat-burning enzyme. They're eating less saturated fat. That's why people eating plant-based diets have higher metabolism, burn more calories while they sleep, because we think of this higher expression of the fat-burning enzyme in our mitochondria thanks to our decreased saturated fat intake. So those eating plant-based diets have less fat clogging their muscles, less insulin resistance. Well, there hasn't been any data regarding insulin sensitivity or how much fat was found in the muscle cells of those eating vegan or vegetarian until now. Research at the Imperial College of London compared the insulin resistance and muscle fat of vegans versus omnivores. Now, those eating plant-based diets had an unfair advantage of being so much slimmer, so they found omnivores that were as skinny as vegans to see if plant-based diets could directly benefit as opposed to indirectly benefit by pulling fat out of the muscles by helping people lose weight in general. They found significantly less fat trapped in the muscle cells of vegans compared to omnivores at the same body weight. Better insulin sensitivity, significantly improved beta cell function, right? The cells in the pancreas that make insulin in the first place. They conclude that eating vegan is not only expected to be cardioprotective, right, prevent our number one killer, heart disease, but that veganism is beta cell protective as well, helping us prevent our seventh leading cause of death, diabetes. This is a graph of fasting blood sugars in the 13 years prior to the onset of diabetes. Insulin resistance starts over a decade before diabetes is actually diagnosed, as blood sugar levels slowly start creeping up. And then, all of a sudden, the pancreas conks out and blood sugars skyrocket. What could underlie this relatively rapid failure of insulin secretion? At first, the pancreas pumps out more and more insulin, trying to overcome the fat-induced insulin resistance in our muscles, and high insulin levels can lead to accumulation of fat in the liver, called fatty liver disease. Before diagnosis of type 2 diabetes, as fat builds up in our liver, it becomes resistant to insulin too. Normally, the liver is constantly producing blood sugar to keep our brain alive between meals. But as soon as we eat breakfast, though, the insulin released from the meal normally turns off liver glucose production, which makes sense. We don't need it anymore. We're not sleeping. But filled with fat, the liver becomes insulin resistant like our muscles do, and they don't respond to that breakfast signal. So keep pumping out blood sugar all day long on top of whatever we're eating. So the pancreas pumps out even more insulin to deal with the high sugars, and our liver gets fatter and fatter. That's one of the twin cycles, the twin vicious cycles of diabetes. Fatty muscles, in the context of eating too many calories, leads to a fatty liver, which leads to an even fattier liver. And this all starts before diabetes, right? But then the next vicious cycle starts. Fatty liver can be deadly, so the liver starts trying to offload the fat by dumping it back into the bloodstream in the form of something called VLDL, and that starts building up in the cells of the pancreas that produce the insulin in the first place. So now we know how diabetes develops. Fatty muscles leads to a fatty liver. It is now clear that type 2 diabetes is a condition of excess fat inside our organs. The only thing that was keeping us from diabetes, from unchecked, skyrocketing blood sugars, is that the pancreas was working overtime, right, pumping out extra insulin to overcome insulin resistance. But as the so-called islet or beta cells in the pancreas are killed off by the fat buildup, insulin production starts to fail, and we're left with the worst of both worlds. Insulin resistance combined with a failing pancreas. Unable to then overcome the resistance, blood sugar levels go up, and we have type 2 diabetes. You may want to have to watch that a few times to kind of fully digest that. There's a lot of technical detail, but if any questions remain, please feel free to contact me through nutritionfacts.org.